Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the next topic for the summer weather training series. We're going to talk about air masses today, and judging by this cover picture, there's a lot of different air masses that impact the United States, and we will delve into the topic of air masses, first introducing what exactly an air mass is, followed by a description of the various types of air masses, which are abbreviated by the initials on this particular image. And then we will go into specific characteristics between summer versus winter. So, as far as a background goes for air masses, just keep this in mind, that some regions of the Earth, they have what's known as weak pressure gradients, where the wind is very light. And that weak pressure gradient occurs at various times that allow for little air movement. So when we have a weak pressure gradient, we have very little wind blowing across the Earth, and we have regions like that. Now the air lying over these particular regions eventually takes on certain characteristics of temperature and moisture specific to that region. And air mass characteristics, they include a combination of both temperature and moisture. So air masses basically can be described as warm, cold, moist, and dry. Now eventually these pressure systems are going to move air masses great distances away from what's known as the source region. And I'll talk a little bit more about the source region shortly. But in general, when you have these air masses building up, eventually you get these disturbances in the mid-latitude westerly winds that are generated due to differences in temperature associated with the specific air masses, which then you get cyclones to develop and frontal boundaries to develop, and then these systems move across the United States, and that then in turn moves the air masses out of their source regions into different parts of the country. What exactly is an air mass? An air mass is a body of air that extends over a large area, and it's usually 1,000 miles across or greater distance than 1,000 miles even. These air masses are going to develop in areas of light winds, as I previously mentioned. Air mass development is not very favorable in areas with a lot of wind, a lot of mixing in the atmosphere. So air masses tend to develop in areas of light winds, associated typically with high pressure. Now, high pressure usually is associated, especially as you get close to the center of it, with what's known as weaker pressure gradients. Now, source regions, the area where these air masses form, have surface terrain with very little changes. So I'm usually looking for a surface terrain that is relatively flat, as an example. Not a lot of terrain changes across the landscape. There's two primary factors in air mass development. These include a surface whose properties, both the temperature and moisture, are relatively uniform throughout the air mass. And an example of a great surface that would meet this criteria would be a water surface over our ocean areas of Earth, our land surfaces, or even snow-covered areas. And second, the other factor is we want a large divergent flow. Divergent meaning the air spreads apart, and that divergent flow tends to destroy temperature contrasts and produces a homogeneous or very similar mass of air. For the development of an air mass, another condition is necessary. This is the equilibrium between both the ground surface and the overlying air. And this is established by the combination of what's known as a turbulent convective transport of heat upward into the higher levels of the air. That's going to transport heat to the higher reaches or upper areas of the atmosphere. Additionally, we can have something known as cooling of air, that radiational cooling, where you have loss of heat from the Earth's surface at night. And then the transport of heat via evaporation, when we change a water state from a liquid to a gas, and then via condensation, when we turn that liquid water or the vapor into a liquid. That's a condensation process. Now, the fastest and most effective process would be the turbulent convective transport of heat vertically, and that is because there is a much more accelerated mixing of the air mass. The slowest and least effective process is radiation, because radiational cooling tends to be more shallow in nature. Now, the circulation effects in air mass formation, we need to talk about three main circulation effects over Earth. One of those would be anticyclonic circulation. The next would be a cyclonic circulation, like you see around low pressure systems in the northern hemisphere. And then these belts of convergence, or converging air belts. Now, with anticyclonic systems, these have stagnant or slow-moving air, which allows time for air to adjust to its heat and moisture content, the temperature and moisture content, to that of the underlying surface. So when these high pressures, for example, come down out of Canada in the wintertime, they initially start out very cold and dry, but as those high pressure systems move down southeastward into the lower 48, generally we have the air mass modifying. I'll get more into modifying air masses here shortly. Now, anticyclonic systems have a divergent airflow, and again, divergent is just a fancy word for saying that the air is spreading apart. All right? And that is going to allow for a larger dispersion or a larger area being covered in the horizontal when you have this divergent airflow. Now, turbulence and convection, and typically we see a lot of that during the heating time of summer. Again, when we're talking about air mass, getting similarities in the air mass, turbulence and convection are going to distribute these properties in the vertical. Subsidence is a way of saying the air is sinking in the atmosphere. This is favorable for lateral mixing, side-to-side mixing, which results in horizontal or overall layer homogeneity, all right, or similarity. Warm highs, such as the Bermuda High over the Atlantic Ocean, as well as the Pacific High, they extend to great heights. And we talked about warm core highs in the last week's training. So when you have a subtropical high or a warm core high, your overall extent at which the air is circulated is going to be much greater. You're going to have a lesser, denser gradient aloft, resulting in an air mass of relatively greater vertical extent. Whereas with cold highs, I want you to think of cold highs as being shallow. An example would be the Siberian high in the wintertime. Very shallow vertical extent because the air is so cold and dense. And that very dense air, in conjunction with gravity, likes to, since it's heavier, basically hug the Earth's surface. This results in air masses of moderate or shallow height. So a couple differences as far as the effects on air mass formation as far as circulation goes. Now, cyclonic systems, on the other hand, they're not conducive to air mass formation. Why? Because cyclonic systems, or these areas of low pressure, are characterized by greater wind speeds or a much greater pressure gradient, which results in a lot of mixing of the atmosphere. And with air mass formation, we do not want mixing. We want very light winds. So these wind speeds associated with cyclonic systems or low pressure areas, they just do not allow for stabilizing process of the air mass. So you get these belts of convergence as well. Now, the belts of convergence or converging air, they're normally not conducive to air mass formation as well, since they generally have the same properties as cyclonic systems. Whenever you have converging belts of air, that air is going to tend to converge in the low levels of the atmosphere and then rise up in the vertical. So again, it's not a very stable situation. So you're looking for atmospheric stability. So there's two areas of convergence where air masses form. As far as when we talk about belts of convergence, these include the area over the North Pacific, basically between Siberia and North America, and off the Atlantic coast of Labrador and Newfoundland. And these areas act as source regions for what's known as maritime polar air, MP air, and we'll get into the discussion of specific air mass characteristics shortly. But just keep in mind that these areas of convergence are typically associated with the Alaskan low, or sometimes known as the Aleutian low, named after the Aleutian Islands in Alaska, as well as the Icelandic low over the North Atlantic. All right, so now let's get into a discussion on source region. The bottom line, a source region is the area at which it's generally the area where air mass is going to form. Now, ideal air mass production is going to occur when the air just stagnates over a relatively uniform surface, which would be, for example, water and land, snow-covered areas. That uniform surface with uniform temperature and humidity, that's what we're looking for. Now, the length of time an air mass stagnates over its source region, or the area where it develops, is going to depend upon the surrounding pressure. The graphic in the lower right of this slide shows the various air masses, and I again will get into more specifics of what each of these air masses, what their characteristics are shortly, and the general paths, especially when we talk about over the United States and impact on our weather. Now, if you look at, for example, over the continent of Siberia or over Asia, the Siberian high pressure system, that's quite common in the wintertime. In addition, you get more of the maritime tropical air, which generally comes into the eastern United States around the circulation of the Bermuda High, producing that hot and humid weather over the eastern U.S. And so there's a lot of different source regions. We'll get into that here shortly. So here, air mass types. Let's now go down into the specific air mass types. We'll start with Arctic air. It's abbreviated by the letter A. And this is associated with permanent high pressure in the vicinity of the North Pole. And we talked about the three-cell theory, or the overall large global cell circulation. And we talked about the polar cell. And generally, air tends to sink over the North Pole at 90 degrees north latitude. And so a sinking air motion that generally tends to lead towards higher surface pressure. Now, in this region around the North Pole, we have a gentle flow of air over the polar ice fields, which allows an Arctic air mass to form. So very light air motion, which is one of our ideal formation mechanisms for air masses. Now, this air mass is dry aloft and very cold and stable in the lower levels. There's just not much moisture associated with high pressure in general because the air is sinking, and as that air sinks, it dries out. Antarctic air, also represented by the letter A. Just keep in mind that Antarctica is a great source region for intensely cold air masses that have continental characteristics. Why? Because over the ice caps, general snowpack, it's very cold in the low levels of the atmosphere, and it tends to have the continental characteristics over these areas. As Antarctic air moves over water, prior to reaching other land areas in the southern hemisphere, it's going to modify into more of a maritime polar or MP air mass, because as that cold, dry air comes down off the higher elevation of those ice caps, it's going to pick up the moisture as it moves over it, and that's going to result in more of a modified air mass to maritime polar air. Now, temperatures in Antarctica are the coldest. They're colder over Antarctica than over the Arctic regions, and the Earth's coldest temperature was actually observed at the Russian research station, the Vostok station, where the temperature dropped to an incredible, can you believe this, negative 128.6 degrees Fahrenheit. That is the world's record for the coldest temperature. Moving on now to a discussion on continental polar air masses. This is abbreviated by the letters CP. Now, these source regions include all land areas which are dominated by the Canadian as well as the Siberian high pressure cells. And in the wintertime, these regions are covered by snow and ice in general. We go up to Canada as well as over Siberia, northern Asia. It's going to be covered by snow and ice. Now, due to the intense cold and the fact that we have this lack of water bodies available, there's going to be very little moisture that's taken into the air in these regions. And I want you to think of polar air generally being found between the 40 and 60 degree latitude marks, and it is generally warmer than Arctic air. Now, the only exception to that is across northern and central Asia. where temperatures can be extremely frigid. For maritime polar air, this is abbreviated by the letters MP. The source regions consist of the open, notice this, unfrozen polar seas, higher latitudes waters that are unfrozen, in the vicinity of the 60 degrees north and south latitude lines. Now, these areas are sources of moisture for polar air masses. Air masses forming over these regions then are moist because they're forming over the unfrozen waters. So they tend to pick up moisture. But the amount of moisture is going to be sharply limited by the cold temperatures. Just keep in mind that cold temperatures can hold much less moisture than the warm temperatures. For continental tropical air mass type, CT, the source regions can be any significant land areas lying in the tropical regions, generally located between 25 degrees north and south latitude. So we're talking very hot land surfaces in the tropical areas of Earth. That's where you'd find continental tropical air. Continental tropical being hot and dry. Now there's large land areas that are located in these particular latitude belts, and these are usually desert regions, such as the Sahara, the Kalahari, the Arabian Desert, as well as in the southern hemisphere, the outback of Australia, that desert area. And again, with continental tropical air mass, it's hot and dry. Now, before I move on, I'm gonna briefly hit two characteristics of each air mass. I'm gonna go back here. Continental tropical air mass is hot and dry. Maritime polar air mass is cool and moist. Continental polar air mass is cold and dry. And Antarctic air and Arctic air is very cold, frigid temperatures, below zero normally, less than 0 degrees Fahrenheit, and it's dry. Okay? And then for maritime tropical air, this is abbreviated by the initials MT. The source regions are large zones of those tropical seas or tropical waters along the belt of the subtropical anticyclones or high pressure systems, such as the Bermuda High. Now, these high pressure cells in the subtropics tend to stagnate in the similar area most of the year, and this air mass is going to be warm and moist. And yes, you can blame it on maritime tropical air if you do not like heat and humidity, because that's exactly what happens along the eastern United States during the summertime when we get the maritime tropical air mass to pretty much dominate the weather day after day after day. And then equatorial air is abbreviated by the initial E. The source region is even closer to the equator. It covers 10 degrees north and south latitude. Essentially, it's an oceanic belt that is extremely warm and moist, just extremely muggy. From experience, I've been down to right around the equator area on a ship, and as well as Guam, and it is, you just go outside and even walk, and your shirt is soaked from the amount of tropical moisture in the air, the equatorial air. Now, the convergence of the trade winds, or when the trade winds come together from both hemispheres, as those trade winds converge, the air rises. You get this intense insolation or incoming solar radiation. The sun is high above the horizon throughout the entire year. And as that heating occurs through the intense insolation from the sun, you're going to get lifting of unstable moist air to high levels, and thunderstorms are quite common. I saw a lot of cumulus, towering cumulus, and cumulonimbus thunderstorm clouds on previous visits to Guam, as an example. Now, the weather is going to be characterized by thunderstorms throughout the year, and that's going to be an association where those trade winds come together. That's going to be an association with what's known as the Intertropical Convergence Zone, ITCZ, or sometimes it's known as a Near Equatorial Trade Wind Convergence Zone. Okay, and again, the importance of the trade winds converging from both hemispheres. Generally, you can get disturbances that come off this belt of thunderstorms, the ITCZ, which can generate a new tropical cyclone with time. And the last but not least, superior air is abbreviated by the letter S, and this is a high-level air mass found over the south-central United States, and the air mass occasionally reaches the surface because of the subsidence or sinking effects. The warmest air mass on record occurs due to superior air. Right, so now that we kind of introduced you to a few topics, let's now move into air mass classification. Now, geographical classification is one of the types of classification we use, and this refers to the source region of the air mass. And it's divided into four basic categories: the Arctic or Antarctic, a polar area, tropical area, and then equatorial area. And then the Arctic, the polar, and the tropical classifications are further broken down by moisture content. Now, air mass is considered maritime if its source region is over an oceanic surface or a water surface. So if I say I have a maritime air mass, right away you should be thinking that air mass is forming over a water body. An air mass is considered continental, on the other hand, if its source region is over land. So when I say continental air mass, immediately you should be thinking that this air mass is forming over land. Now, equatorial air is found exclusively over the deep, low-latitude tropical waters in the vicinity of the equator. Now, with air masses, there's something that we need to discuss, because the air masses never stay the same. All right? They may have certain characteristics of temperature and moisture within the source region, but then as these air masses move out of that source region, they're going to move over moister or drier areas, warmer or colder surfaces below them. And that is going to act to modify the air mass over time. So we talk about thermodynamic. Thermodynamic classification is going to apply to relative warmth or coldness of the air mass. Now, for example, a warm air mass is abbreviated by the letter W. This is going to be an air mass that's warmer than the underlying surface. A cold air mass is abbreviated with the letter K, and this is colder. This air mass is colder than the underlying surface. So as an example, if I had a continental polar air mass, a cold, dry air mass, moving over a warmer surface, it would be classified as these three letters, C, P, K. C representing continental, so we know the air mass formed over land. P representing polar, so we know we have a colder air mass. And K represents the thermodynamic classification, with K being an air mass that is colder than the underlying surface. Or in other words, the air mass is colder than below. The surface below the air mass is warmer. That makes sense. And then a maritime tropical air mass moving over a cooler surface would be classified as what's known as MTW. M meaning maritime, T tropical, and then W indicating that the air mass is over a cooler surface. The air mass is actually warmer than the surface. Now, you can tell a lot by clouds. And I've given previous training lectures on the Spot On Weather YouTube channel. Clouds are the language of weather. If you can look at the sky each day and see what type of clouds you have, you can become an expert forecaster. Clouds and air masses are going to vary. The different types of clouds are associated with different air masses, and it's really awesome if you can just go out there and identify those clouds. You can actually tell what type of air mass you have in your area for that day. So air masses can definitely be identified by the cloud types within them. For example, colder air masses are usually going to show more of the cumulus clouds, or those puffy clouds, whereas warm air masses are usually going to contain the stratus clouds, the very layered-like clouds. Now, the thermodynamic classification, which we just talked about here, right? Whether the air mass is warmer or colder than the underlying surface, W versus K, that may change between night and day. That a particular air mass may show these K characteristics during the day, and then these W characteristics at night, and vice versa. Here's a great chart that breaks down the air mass classifications. Okay. In general, you see the designator starting with CAK, continental Arctic, which is colder than the underlying surface. CAW, you have MAK, which is maritime Arctic, all the way down to superior air at the bottom. So this just shows you, this is more of the thermodynamic descriptors once again. The last letter, whether it's warmer or colder than if the air mass is warmer or colder than the underlying surface. So this is just a really great graphic to take a look at. Modification. So now we're going to talk about, as these air masses move out of their source regions, what is going to happen. So for example, an air mass in wintertime, it's going to come down out of Canada, and it perhaps may have below normal or below zero temperatures. Okay? By the time it reaches Southeast Virginia or the Mid-Atlantic as a whole, those temperatures may have modified on the order of 20 to 30 degrees Fahrenheit. Okay? So when an air mass moves out of its source region, a number of factors are going to act upon the air mass to change its properties. For instance, a passage of cold air over warmer water surfaces is going to result in a release of heat and moisture to the air. So we have a cold over warm situation. Whenever you have a colder air mass aloft over a warmer surface, that generally leads to instability, where you're going to get more of the cumulus clouds and more showery precipitation. But by the act of those vertical air currents, when colder over warm, the air is going to rise in the vertical. That's going to modify the properties of that air mass. The type of the surface the air mass travels over is very important. The factors include surface temperature, moisture properties of the underlying surface as the air mass comes out of its source region, as well as the topography. The topography refers to the elevation changes or air masses crossing mountainous terrain. And that's going to also modify the air mass significantly. Now, the type of trajectory the air mass takes, whether it's a cyclonic or counterclockwise trajectory or an anticyclonic, which is a clockwise trajectory out of its source region, also has a bearing on the air mass modification. And then additionally, how long, or the time interval, has the air mass been out of its source region? For example, when it first comes out of its source region up in that northern part of the U.S. in the winter, temperatures are going to be frigid. But 3 days later, it may be sitting over the southeastern U.S. coast, and it's going to be much different characteristics based on the modification. So let's first talk about temperature modification. Now, the difference in temperature between the surface and the air mass modifies not only the air temperature, but also the stability of the air mass. And this is what we get down to talking about the cloud types associated with the air masses. If the air mass is warm, for example, and moves over a colder surface, such as tropical air moving over colder water, colder land, that colder surface from below is going to cool the lower layers of the air mass, and that stability of the air mass is going to increase. So just like I talked about in the preceding slide, I talked about colder over warmer usually yields instability. Warmer over a colder surface, warm over cold, yields stability. So this stability is going to extend to the upper layers in time, and you'll get this condensation where your water vapor, your invisible water vapor, it condenses out into liquid form as far as cloud droplets. And that's going to, usually the weather associated with a stable air mass where you have warmer air aloft over a cooler surface, that's going to be, you're going to see a lot of fog or low stratus clouds. Now, if the air mass moves over a warmer surface, such as continental polar air moving over warmer water or heated land, the warmer surface is going to heat the lower layers of the air mass. You have a cold over warm situation, which yields greater instability. So you're going to get cumulus clouds now in this case, greater vertical air motion, much more accelerated, depending on the temperature difference between the surface and the overlying air. Now, changes in stability of the air mass is going to give valuable indications again of those cloud types that will form, as well as the precipitation type to be expected. The increase or decrease in atmospheric stability will give further indication of the lower layer turbulence and visibility. Here's some examples, some good graphics here to show you. Temperature modification of air masses. Initially, we have warmer air, the air moving over eventually colder surfaces. And you notice how the colder air over warmer land yields these puffy clouds in the left-hand portion of the diagram. And then as that air mass, the cooler air mass moves over a colder surface, that's generally going to yield more of the way of stratus clouds or fog or much more instability in the atmosphere. Another example shows colder air coming off the continent. Generally, we see as that cooler air moves over a warmer ocean surface, we get more in the way of much more taller cumulus clouds and showery precipitation. This happens a lot off the east coast of the United States when you get the cooler air masses moving over that warmer Gulf Stream current. Now, that was temperature modification, but now let's talk about surface moisture modification. An air mass may be modified in its moisture content by the addition of moisture as a result of what's known as evaporation, where the liquid surface liquid is evaporated and changes to a vapor, or by removal of moisture as a result of condensation and precipitation. When the atmosphere rains, it generally dries things out. Okay, so if an air mass is moving over a continental region, a land area, the existence of unfrozen bodies of water, they're going to greatly modify the air mass. It's going to allow much more evaporation to occur. It's going to add for a more moist air mass downrange. Now, dependent on the temperature of the two surfaces, the movement over a water surface is going to increase both the moisture content of the lower layers and the relative temperature of the surface. Water will definitely, air mass moving over a water surface will definitely add the moisture, but also you got to think about the temperature. Water has more of a modifying characteristic on temperature. So the passage of cold air over warm water, that's going to decrease the stability of the atmosphere. You're going to get a lot more rising vertical air currents. And meanwhile, the passage of warm moist air over a colder surface, think about the opposite effect. It's going to increase the stability, warm over cold, and could result in fog as the air is cooled and moisture is added via evaporation. And then lastly, we need to talk about the mountains. They play a huge role in air mass modification. Living around the mid-Atlantic area, especially if you live down in southeast Virginia, you're very familiar with this. Because in wintertime, you get extremely cold air that's going to come out of Canada, continental polar air, and maybe you have some moisture along a leading edge of a cold front. And that moisture, that front's going to move up, and the air mass is going to move up against the windward side of the Appalachian Mountains. And as it does this, on the windward side of the Appalachian Mountains, the air is going to rise. All the moisture, the precipitation is going to fall out of the cloud, most likely in the form of snow in the wintertime. And then when the air sinks on the east side of the Appalachian Mountains, the leeward side, the air mass is going to, number one, the temperature is going to be milder on the leeward side, because as air sinks down the mountain slope, it's going to warm and dry out. So drier and warmer, milder conditions usually happen across southeast Virginia because of the orientation to the west of those Appalachian Mountains. So the effect of topography is huge. Additional modifications occur across the western United States when we talk about the Rocky Mountains. So the air mass is modified primarily on that windward side by the removal of moisture. Everything precipitates out on the windward side of the mountain range with a decrease in stability. The air is rising in the vertical, but as the air comes down again the other side of the mountain range, the stability is going to increase. As the air sinks, it warms and dries out, becomes more stable, and there you have it. The trajectory modification. After air mass has left its source region, the trajectory it follows, whether it be cyclonic or anticyclonic, has a great effect on its stability. Generally, if the air follows more of a cyclonic trajectory, its stability in the upper levels is going to be decreased, whereas the instability is a reflection of cyclonic relative vorticity. So again, if the air mass makes a cyclonic trajectory out of the source region, we're going to have decreasing stability. Okay. Now, if the trajectory out of the source region of the air mass is more anticyclonic or clockwise, and I'll show you some maps here shortly, if that trajectory is anticyclonic, its stability in the upper levels is going to be increased as a result of this subsidence or sinking air motion that's associated with this anticyclonic relative vorticity. And then air mass age. The age of the air mass determines the amount of modification that takes place. For example, an air mass that has recently moved from its source region cannot have the time to become modified significantly. Whereas an air mass that has moved into a new region and stagnated for some time, it's now going to become older and take on the new characteristics of its underlying surface. So if we put everything together, what we talked about so far, and we look at thermodynamic, right, and that had to do again with the air mass in relation to the underlying surface, whether that underlying surface is warm or cold, as well as mechanical modifications through turbulent mixing of up and down draft of air, sinking or subsidence air motion, or lifting or rising air motion. Here you go. This is a great chart. So for example, if I have heating from below as the air mass moves out, the air mass passes from over a cold surface to a warmer surface, there's a general decrease in stability. But if I have cooling from below, as the air mass moves out of the source region, it's moving over a cooler surface, generally we're going to have an increase in stability. And then we have the addition of both the moisture and the removal of the moisture. If you add moisture, you decrease your stability because moist air is much lighter and wants to rise. Whereas if you dry the air mass out through removal of moisture, you're going to have an increase in stability because the air mass is going to be heavier. And again, the mechanical, turbulent mixing, the sinking air motion is going to increase stability. The lifting of the air is going to decrease the stability. So this is another great graphic just to show you how the air mass modifies. Now, air mass essentials. Okay, I want to talk about a few things here. First of all, the weather within an air mass is controlled primarily via moisture content and that relationship between surface temperature and the air mass temperature overall, as well as the terrain, whether we're talking upslope or downslope motion. Just keep this in mind. When air rises, it is cooled, and descending or sinking air is warmed. And these condensation, where the air changes form, the water vapor changes form from a vapor, invisible water vapor, to a liquid, this takes place when air is actually cooled to its dew point. Now, stability is going to increase. It's going to increase if the surface temperature is lowered or if the overlying air at higher levels is warmed. In any case, we have a warm over cold situation, and we're going to have more stable conditions. As a result, we're going to have these smooth stratus clouds, and you generally can identify these based on, it almost looks like a blanket. And in future training session, I'm going to go ahead and cover all the clouds, and so you get to see the difference in the cloud types. Now, stability is going to decrease. We're going to go to instability, in other words, if the temperature aloft is cooled and you get these turbulent, convective cumulus clouds, these puffy clouds. Now, have you ever walked outside on a hot summer day and noticed how tall these clouds get? That is an indication of atmospheric stability. The taller the clouds get, the higher they build up, the more unstable the atmosphere is. And there's a good chance you could see a thunderstorm later on those particular days when those clouds go really tall. Okay? Now, let's go into the specific North American air masses during the wintertime, and then we'll move into the air masses in summer, and then we'll do one wrap-up conclusion on today's training on air masses. So, first things first, continental polar, remember CPK is continental polar, and it's an air mass which is colder than the underlying surface, and CAK is continental Arctic, which is colder than the underlying surface. Those two air masses over the U.S. are going to depend on the trajectory of the air mass after it leaves the source region. Now, for an air mass to be considered Arctic, the surface temperature is generally 0 degrees Fahrenheit or colder. Now, this is the surface temperature. This doesn't even include the wind chills. And if you look at the graph on the bottom right, this map of the United States, and showing the various types of air masses we see in wintertime. Now, we can have unusual warmth if we get the subtropical ridge to build up to anomalously strong conditions. in case we get the air that comes right out of the Gulf of Mexico up the eastern seaboard, this is the record-breaking warmth of winter, when you get this surge of maritime tropical air from the Gulf of Mexico. Additionally, we can have a Pacific mild flow, where you see the arrow coming right from the Pacific Ocean. Generally, the jet stream is orientated more west to east, and you get more of this mild Pacific air from west coast to east coast. That has occurred. That results in some of the mildest winters. Now, it's not record heat when you have that Pacific mild flow, but it is still mild. Now, you also can get maritime polar air coming down from off the North Atlantic, and that's associated with damp and chilly weather, where you get those really low, dull gray days where it's very gloomy. And then you can have Arctic air coming down from Canada into the eastern U.S., where you get cold. And then you get more of the Siberian air, which basically goes all the way across from Siberia, all the way through Alaska, and then down through Canada into the United States, producing some of the coldest air. This is associated, Siberian air, more with record lows and record cold in general. So this is just a nice look at the different air masses, and the arrows represent the various flows of air masses during winter for the U.S. So let's first talk about continental polar CP air that is colder than the underlying surface, and continental Arctic air, which is colder than the underlying surface. Let's talk about these air masses. So you see there's many different trajectories when this air mass comes out of the source region. Okay, these trajectories, we're going to break down the weather associated with each. So we have a trajectory A, B, C, D, E, F, and G with these particular air masses in wintertime. So trajectory A and B are usually indicative of a strong outbreak of cold air. So you see how it goes into New England and the mid-Atlantic states right from the north, right from Canada. Usually get stronger surface winds of 15 knots or more. And if the air mass takes the A and B trajectory, if this modified air mass moves rapidly over rough terrain, such as Appalachian Mountains, the turbulence results in these low stratocumulus clouds and occasional snow flurries. Now, on the leeward side of the Great Lakes and on the windward side of the Appalachian Mountains, this is when you can expect a low, broken overcast sky condition with frequent and widespread snow showers or these snow squalls. Talk about lake effect snow, where you get this extremely cold air, this continental polar air moving over the unfrozen water, the relatively warmer unfrozen waters of the Great Lakes, and some of the record snowfalls have occurred downwind of these lakes, especially Lake Erie and Lake Ontario, western New York State. New York State's got the snow belts, as well as Pennsylvania into Ohio. You can get some really prolific snowfall amounts when you have this type of trajectory in the wintertime. Places like Buffalo, New York, Syracuse, New York, right? Erie, Pennsylvania. Now, east of the Appalachian Mountains, with this type of trajectory, you get skies that are relatively clear, and you will, on some occasion, get these scattered stratocumulus clouds, which are layered like cumulus clouds. All right, and again, this is the modification of the mountains. By the time this CP, continental polar or continental Arctic air mass reaches Southeast Virginia, for example, the coastal areas of the Mid-Atlantic, it's been significantly modified, and that is a great amount of that is due to those Appalachian Mountains. What about trajectory C and D? So you look at trajectory C and D, it's more of an anticyclonic flow, a trajectory of the air mass out of the source region. This is going down more to the Gulf Coast at C, as well, and D going more over towards the southern plains. So with these trajectories of this type of air, these type of air masses usually get unusually smooth flying conditions that are found, except near the surface, where you get a little bumpiness, a little turbulent layer, which results in what's known as a steep lapse rate and some bumpiness. Now, a steep lapse rate is just a very rapid change in temperature with height. And the faster that temperature changes with height, the greater the risk of turbulence. So if you're flying in a plane, you feel the bumping around in the wintertime, and you're flying anywhere from, let's say, Illinois down to the deep south, maybe points westward into Kansas, Oklahoma, this is most likely associated with one of those strong cold air outbreaks. Now, as that cold air stagnates and eventually subsides, or the air sinks under the influence of this anticyclonic trajectory at C and D, you get more stability. The stability is going to increase, which is going to result in perhaps some haze layers developing, and this is going to indicate the presence of subsidence inversions. This is going to reduce the visibility. It's going to kind of like trap those hazy particles. Now, movement of the continental polar air and the continental Arctic air or westward over the Rocky Mountains to the Pacific coast is actually really infrequent, generally because of how high the Rocky Mountains are and how cold and dense these air masses are. They like to stay close to the ground due to their increased density. So they just really don't get over the tops of the Rocky Mountains and spill on the other side west of the Rockies very often. Now, if we look at continental polar and continental Arctic air masses with trajectory E, now we're kind of going towards the western U.S., right? We're going down into parts of Idaho, eastern Oregon, into California. And in this trajectory, we see rather mild temperatures and low humidity. A drier, a cool and dry air mass occur on the Pacific coast. And this is mainly due to that, what's known as adiabatic warming or sinking air motion of the air flowing down the mountain slopes. And it's going to produce really great flying weather, good visibility, clear skies on trajectory E. Now, trajectories F and G with continental polar and continental Arctic air masses, occasionally the trajectory is going to pass out over the Pacific Ocean. In this case, that's what's happening at F and G. The air is going to arrive over central and southern California as this cold, very unstable air mass. And this is when Southern California actually gets their rain. When you get this cold air aloft that moves, picks up moisture as the air mass moves over that Pacific. So you got moisture, you got, this cool air mass, and that's going to result in stability and some showery precip for Southern California during the winter season. Now, this type of trajectory associated with squalls and the showers, as well as more convective clouds, the cumulus and the cumulonimbus clouds. Lightning has actually, that's the time of year in the winter when you get these cold air surges, cold, moist, unstable air aloft, especially if you get surface heating during the day. Cold over warm situation over Southern California can really produce, thunderstorms. Now, visibility is generally 1 to 5 miles during this heavier showers, and then you actually get snow as far south as Southern California mountains in San Diego County. Looking at the maritime polar air mass now over the west coast in winter, we have trajectories A through D with this discussion. With trajectory A, the maritime polar air mass is going to originate in the Gulf of Alaska, and it's going to be pulled back out over the Pacific, down the Pacific, by a low pressure system, which is generally close to what's known as British Columbia, which is the far western part of Canada. So this air has trajectory A, has a relatively short path over water. And it brings very cold weather to the Pacific Northwest typically, places like Seattle. Now, when the air reaches the coast of British Columbia and Washington State, after 2 to 3 days over the water, it is going to be convectively unstable. So in this case, you're going to get more of those puffy cumulus clouds and atmospheric instability and showery precipitation. The instability is released when the air is actually lifted by the Pacific Coast Range, the Wasatch Mountains, for example. Cascade Mountains, for example. I'm in the wrong state. Cascade Mountains, for example, are going to lift this air mass up, and it's going to reduce in ceilings where the cloud decks are located on the order of 1,000 to 3,000 feet along the coast. A lot of the heavier precipitation is going to fall on the windward side of the Cascade Mountain Range of Washington. Cumulus and cumulonimbus clouds are the primary cloud types extending to very high levels, and you're going to get a lot of icing. And, it's going to be severe in these clouds if you're ever in a plane and flying through them. For trajectories B and C, this is, as you can tell by the arrows, this is a longer overwater trajectory during the winter months at B and C. Now, when there's rapid west-to-east motion and there's small north-to-south motion of pressure systems, this maritime polar air may influence the weather over most of the United States. So this is the type of mild weather pattern when you get a more west-to-east jet stream, where the air at the trajectory at B and C here, the maritime polar air, is basically going to work its way all the way across the country. Because of this longer overwater trajectory, in this case with B and C, this maritime polar air is heated to greater heights and convective instability is present all the way up to about 10,000 feet above the ground. You'll see showers, turbulent gusty winds, these steep lapse rates again where the temperature changes rapidly with height, and then you'll get good visibility outside of showers, and that's quite common. And then trajectory D for maritime polar air masses along the west coast in winter. Now this trajectory is over water long enough to permit air mass modification at all levels. And when the air reaches Southern California there, the Southern California coast, it's going to be very stable with one or two subsidence inversions. Now, what does subsidence inversion actually mean? Subsidence refers to sinking air motion that is associated with high pressure, and the inversion is associated where temperatures are actually warm with height. So we have a warm over cold situation. These subsidence inversions indicate very stable air, and as a result we get this stratus and stratocumulus cloud field to develop along the coast of Southern California during the winter months. It's frequently found with the ceilings of the clouds between 500 and 1,500 feet, with the tops of the clouds less than 4,000 feet. Visibility is generally going to be fair, except during the early morning hours when you can get this haze to develop, and this reduces the visibility at times to less than 1 mile. And then when this maritime polar air mass continues eastward and crosses the Rocky Mountains and encounters a deeper area, a denser dome of continental polar air beneath it, it is forced to overrun it, and this results in storm conditions. This results in blizzards over the plain states east of the Rocky Mountains. When you get a good flow of this cool, moist air, the maritime polar air mass overrunning much colder continental polar air in the low levels, and this can result in blizzards in the southern plain states, Oklahoma, Kansas. All right, now let's move to the east coast for the maritime polar air masses in the wintertime. Being in the mid-Atlantic, living in the coast of Virginia, I have seen this happen so many times in the wintertime. What happens is you get this really strong area of high pressure associated with continental polar air. The air mass is initially cold and dry, but as the air mass moves over the waters of the North Atlantic, these unfrozen waters, moisture is picked up, the temperatures are warmed slightly, and this results in a conversion from continental polar air mass to maritime polar air mass. And it becomes quite significant along the east coast in winter. This occurs when a continental polar air mass, again, the anticyclone or high pressure system, is going to move slowly off the coast of the maritime provinces as well as New England. And again, air that's originally continental polar undergoes less heating than its Pacific counterpart because the waters of the North Atlantic are colder than the waters over the North Pacific. And as a result, you get reduced time over water as well with this trajectory. You get this instability where you have colder over warmer, relatively warmer water surface, but it's confined to the lower layers of the air mass. You get this light drizzle or snow that is typical along with low visibility. And ceilings are very low, generally 700 to 1,500 feet, with tops only up to about 3,000 feet. Flying conditions are rather dangerous in this type of weather scenario because of the turbulence, and you get this icing near the surface. The freezing level is relatively low, not quite to the surface in most cases, but still, if you're in and out of precipitation in a plane flying, you're going to get more icing and even some bumpiness with turbulence. Clouds are usually extended as far west as Appalachians. By the way, when this type of situation occurs with high pressure to the north, you typically get what's known as cold air damming, where your coldest air is heavier and remains east of the Appalachian Mountains. In areas such as Virginia, North Carolina, all the way down east of Atlanta, generally with a cold air damming situation, you get a lot of clouds, that thick, low, gray overcast. Some days it doesn't feel like it's very light out, especially in December if you get this kind of situation when you have short amounts of daylight hours. But generally this happens quite frequently along the East Coast in winter. Now, what about the maritime tropical air masses in winter along the eastern U.S.? Now, the temperature and moisture content are generally going to be higher in the MT air mass because it's warmer, maritime, tropical, it has the ability to hold more moisture when it's warmer, when it's a tropical air mass, as compared to a polar air mass. Now, in the southern states, along the Atlantic coast, when we disregarding frontal action, this occurs quite frequently. So with frontal activity, you get these lines of showers and thunderstorms that develop along the leading edge of a cold front when you have continental polar air coming in from the northwest. And that's going to result in a lot of precipitation, heavier shower activity. Now, if maritime tropical air is forced over mountainous terrain across the eastern United States, the conditional instability that's released at the higher levels of the atmosphere, that's going to result in thunderstorms or a minimum large cumulus clouds, And pilots got to be very aware of this type of situation in winter because these clouds may develop out of just layered-like, stable-looking stratus clouds. And they can be embedded within that stratiform cloud deck and can occur on relatively short notice with very little warning. Now, occasionally, when the land has been cooled along the coastal areas in the wintertime, this maritime tropical air is going to flow inland as that warm, moist air overruns the colder land surface. This is going to produce what's known as advection fog over extensive areas, and this fog is very thick, and it's very common, especially in the Florida Panhandle during the winter season. I have lived down along the Gulf Coast, I have lived around the Pensacola area, and I have personally seen how thick this fog gets around the Pensacola area, this advection fog in the wintertime. Literally, you will have airports shut down because the visibility is less than an eighth of a mile, for example, when this warm, moist air runs up over the cooler land surface of winter in December especially. Ceilings of visibilities are occasionally below the safe operating limits for most pilots. However, flying conditions are relatively smooth once you get above the stratus layer, and icing conditions are absent near the surface layers. So as this trajectory, this clockwise flow or anticyclonic trajectory occurs from the Gulf of Mexico northward, progressively over colder land, the surface layers are going to cool and become saturated, and that's what really socks areas in with dense fog. This cooling is greatly accelerated if the surface is snow-covered, or if this trajectory carries this warm, moist maritime tropical air over a colder water surface. Now, you get fog with light winds. They form rapidly. It forms very quickly, folks, because of the surface cooling from below, the saturation from below. And occasionally you get little mist droplets or this drizzle, very small diameter, just seems to float in the atmosphere, in the air, with very poor visibility. And sometimes you get frontal lifting. As this maritime tropical air eventually moves towards the mid-Atlantic, if you have a frontal boundary there coming down from the north with continental polar air trying to push south, these air masses converge along that front, and you can actually get quite a storm system with steadier precipitation, and it can be quite heavy in the form of rain or snow. Here's a look at some examples of maritime air masses in wintertime. Initially, the graphic on the left shows the motion of the maritime tropical air mass from the southwest toward the northeast. Initially, over the Gulf of Mexico, we have 68 degree Fahrenheit water. So here comes the maritime tropical air mass moving over a 10 degree Celsius or 50 degree Fahrenheit surface. As soon as that warm, moist air moves over the colder land surface, you get a lot of drizzle and fog and low stratus, very low visibilities along the Gulf Coast, especially the Florida Panhandle. And then if that maritime tropical air mass is forced up and over the windward, the western side of the Appalachian Mountains, it can result in these unstable conditions where you get thunderstorms and heavier showers. It could be rain showers and snow showers over the Appalachian Mountains. The graphic on the right shows, again, air drawn by the arrow there, indicated by the arrow, air moving from the warmer surface to the colder continent, and that is going to reduce and greater stability and the development, again, of that low fog or the low stratus cloud. So here's a summary of winter air masses in general that affect the United States. You have continental polar air masses, maritime polar air masses, maritime tropical air masses. Now, I didn't mention maritime tropical for the Pacific coast or the western U.S. Because it's very rare that the maritime tropical air makes it into the United States off the Pacific Ocean in the wintertime. But this is a great chart. Generally shows you the impacts of the air masses on clouds, the type of clouds you would see, where the layers are at, how high they are off the ground, the ceilings, the visibilities, whether the visibility is good or bad in the respective air masses, as well as turbulent air motion, and then the surface temperature of the air masses. Important points here: continental polar air mass moving southeast of the Great Lakes, downwind of the Great Lakes, you're going to get these massive bands of lake effect snow, which is going to produce sometimes record-breaking snow amounts. And maritime polar air from the west to the east coast, that generally results in milder conditions, above normal temperatures in the wintertime across the U.S., when you get more of a west to east jet stream trajectory. And then maritime tropical air, that's going to bring in warmer and moister air from the Gulf of Mexico. Right, now let's turn our attention to the air masses of summer. With the air masses of summer, we'll start first with the continental polar air masses. They're quite different from the continental polar air mass in the wintertime. Because of the longer daylight hours, a higher altitude, the sun is higher above the horizon, as well as the absence of any snow-covered ground over the source region, this air mass is usually unstable in the surface layers. In contrast to the marked stability found in continental polar air at its source in winter. Now, typically you get clear skies or these scattered puffy cumulus clouds with continental polar air masses in summer with unlimited ceilings. Additionally, when this air reaches the central and eastern U.S., it is characterized by early morning ground fogs, or you might find this low stratus or stratocumulus cloud decks in the morning. Visibility is generally good outside of haze or ground fog near sunrise. So continental polar air, this is the air mass that gives us the break from this, from the high humidities along the east coast of summer. And you may see some scattered cumulus clouds. On days we have continental polar air, generally the air mass is more stable, and the growth of those cumulus clouds is in the vertical is much less. They have more of a flatter appearance. So convective activity of continental polar air in the summer, generally confined to the lower 7,000 to 10,000 feet. Flying conditions are generally smooth above 10,000 feet, except when you get these local showers to develop. And the base of cumulus clouds that form in this air is relatively high, 4,000 feet, because of the drier air mass and the low levels of the atmosphere. This is a case where dew points can drop into the 60s for many parts of the eastern U.S. cities. When you get continental polar air to move in, gives you a break from those muggy 70-degree plus dew points. Now, what about maritime polar air masses in summer along the west coast? The entire west coast is going to be dominated by the maritime polar air mass in the summer. You get this fresh inflow of maritime polar air over the Pacific coast, and typically what you see is clear skies or maybe a few scattered cumulus clouds, generally observed over the coastal mountains. As this air flows southward along the coast, you get a marked turbulence inversion reinforced from aloft. Stratus or stratocumulus clouds generally form at the base of this inversion. Ceilings are typically 500 to 1,500 feet, especially in Southern California, with tops seldom above 3,500 feet. And you get the formation of stratus along the coast of California. This is greatly enhanced by the presence of what's known as upwelling, cold water along the coast. And I haven't really talked about ocean currents in any of my training to this point, but just keep in mind that you have a colder north to south flowing California current along the western U.S. coast. This trajectory of the maritime polar air pretty much parallels that California current as it moves down the coast. Now, what happens with time is the California current, that colder current is directed outward away from Southern California, and as the surface layer the wind blows clockwise around this eastern Pacific high, and that surface layer water is taken outward, further seaward, away from the Southern California coast, and below, some cooler water comes up to the surface to replace that top layer water that has been pushed out to sea. This results in what's known as upwelling, in which you get this really cooler water from below that comes up, and this maritime polar air, that wind flow moving along over that air, that cooler water is going to generate warmer over colder situation. The air mass is warmer than the underlying colder current, colder water, and that's going to result in a lot of stratus and even fog along the coast of Southern California and in parts of the Central California as well. Now, the maritime polar air masses on the East Coast in summer, a lot different. In spring and summer, maritime polar air is occasionally observed over the East Coast. And when this happens, we'll get into a training topic on fronts, but there's something known as a backdoor cold front, and this is a case in which the maritime polar air is going to move in with northeast winds off the North Atlantic into the East Coast and the Mid-Atlantic especially. And this is going to result in cooler temperatures, especially in springtime. Temperatures can be pretty cool with highs in the 50s and 60s. Generally, with a maritime polar air mass with this type of trajectory off the North Atlantic waters, you have marked drops in temperature that frequently bring relief from heat waves with these backdoor cold fronts. And again, I will tell you from experience that it's a refreshing change if you get this a wind shift from the southwest to the northeast with this maritime polar air moving in off the Atlantic. Ceilings are generally low, between 500 and 1,500 feet. Tops are not very high at all. So you have some marginal VFR conditions if you're a pilot flying through it. No precipitation generally occurs with these cloud tops or types, and visibility is usually good. So with this case, you usually have very stable layer of air. If anything, you might get a little drizzle. This is a case where the sky looks dark and you're thinking it's going to pour, rain, and nothing happens. All right? Nothing happens with this. As far as copious amounts of precipitation, with the stratus layer, things are just too stable. Not much rising motion in the atmosphere in the vertical. As far as maritime tropical air masses in the summertime, oh boy, this is the air mass that is responsible for all that nasty heat and humidity. Maybe you do like that heat and humidity, but maritime tropical air masses in summer, this influences the eastern half of the U.S. big time, almost day after day, especially when we get into the months of July and August, where we get the subtropical high pressure, that Bermuda high, directing the winds to come in, the maritime tropical air mass to come in from the Atlantic Ocean like this. Warm, very warm air mass, very muggy. In summer, you get convective instability, where you get the land's heating much more greatly, especially in July and August, and you can get daily thunderstorms to develop. This air is very warm, moist, it's very buoyant. It has a tendency to want to rise in the vertical. So initially in the morning, things are fairly stable. You get development of these early morning stratocumulus or layered clouds along the coastal areas. The clouds tend to dissipate during the middle morning and then reform into the shape of cumulus clouds during the heating of the day. Especially by early afternoon, you'll start noticing the cumulus puffy clouds develop. And the continued development of the cumulus clouds leads to scattered showers and thunderstorms during the late afternoon. So very common. The ceilings and the stratocumulus clouds in the morning, they're generally favorable for flying. They'll range from 700 to 1,500 feet. The ceilings eventually become unlimited as that stratiform layer dissipates. You get the development of a cumulus cloud due to the heating. The air's rising over the heated land. Flying conditions are usually favorable since convective activity is scattered in nature. And so, even though you might get thunderstorm development in the late afternoon hours, the maximum time of heating with this type of air mass in the summer along the East Coast, pilots are still, they can still circumnavigate around these thunderstorm cells. It's not a very widespread coverage of thunderstorms. It's more scattered in nature. Visibility is generally good except near sunrise, when the air is relatively stable over the land. And you get extensive sea fogs that can develop whenever this air flows over a relatively cold current in the far northern Atlantic. So, the notorious fog over the Grand Banks of Newfoundland is usually formed due to this process. Anytime you get warm, moist maritime tropical air moving over colder waters in the ocean, you're going to get saturation from below and very thick fogs. All right, I've seen this on the Pacific side too. You know, I've been on a ship that's gone from Hawaii all the way up to the Bering Sea in the months of July and August, and the Bering Sea is just socked in fog day after day because you have this warm, moist, empty air mass moving over the colder waters there of the Bering Sea. And then lastly, about empty air masses in the summertime. In late summer, just a word of note here, the Bermuda high, that subtropical high, is going to intensify. It's going to result in a flow of empty air. I'm not showing it here, but if I went further west on the map, this maritime tropical air actually makes it over to Texas, New Mexico, Arizona, Utah, Colorado, and even Southern California at times. You can actually get what's known as monsoonal moisture associated with this maritime tropical air mass moving in to the southwestern United States. You already have intense surface heating in the desert southwest during the months of July and into August. And then you also get sometimes orographic lifting due to higher elevations. And so you can get showers and thunderstorms prevailing over the southwestern U.S., over those desert areas. This is locally known as Sonora weather. Continental tropical air mass this summer. This is found generally over the U.S., and it's only going to be in the summer season. Its source region is the relatively small area over the northern portion of Mexico, West Texas, New Mexico, and eastern Arizona. It has high surface temperatures and very low humidity, very dry air mass, hot and dry, large daily changes in temperature, a large range of temperature change. Okay, and absence of precipitation are additional properties of continental tropical air. Flying conditions are excellent outside of, you get this occasional daytime turbulence extending from the surface. Especially if you get close enough to the surface, you might feel a little bumpiness due to the intense heating of the landmass. So again, this is a case where, you know, continental tropical air, you may have in Phoenix, for example, you may have a low temperature in the 60s and a high temperature 105 to 115 degrees Fahrenheit in the heart of summer. Here's a summary of the summer air masses, continental polar air masses, as well as maritime polar air masses, maritime tropical air masses as well. And that wraps the training up on air masses today. I know it was a little bit lengthy, but I certainly appreciate your attention. I hope you learned something from today's training on air masses. They're very important, the air masses. Wherever you live in the United States, if you can just take a look at the sky every day and know what type of cloud is in the sky, whether it be a cumulus cloud where it's puffy, or more of a stratus cloud where it's layer-like, you generally know what kind of air mass you're in, really. For example, the maritime tropical air mass during the summer season here in Virginia, it's very common to see these puffy cumulus clouds day after day. In addition, you would look at the characteristics of what the surface dew point is. Generally, if the surface dew point is above 60 degrees Fahrenheit, 60 degrees, generally that indicates a maritime tropical air mass. In general, wind direction, it does play a lot into the transport of these different air masses. For example, if I get a southwest wind in the summertime, I am getting maritime tropical air mass from the Gulf of Mexico coming into Virginia. Whereas if I get a northeast wind in the summertime, I'm actually going to get a break from all the heat and humidity. I'm going to get more of a maritime polar air mass moving in. And if I get a northwest wind in the summertime, I know that I'm getting more of a continental polar air mass from Canada. And in general, the predominant wind flow, the predominant air mass, they all kind of tie in together. More of a southwest wind flow is predominant in Virginia in the summer, or along the east coast in the summer. And then you get more of a maritime tropical air mass. Whereas winter, you get more of a northwest or northerly wind, transporting that colder, drier continental polar air into the area. But again, air masses really help to explain a lot of what you're feeling when you walk out the door in the morning. Really important. All right, that wraps things up on the training. Thank you so much for subscribing to the Spot on Weather YouTube channel. We'll be back again with more training as we're getting ready to close out the month of July and head into August. And then as we get into the fall, we'll be looking at issuing our winter forecast, which we know is very popular among our subscribers. All right, we're Spot on Weather. If we're not spot on, we're not doing it right. Hopefully you enjoyed the training. Take care, everybody, and God bless.